Now that we have learned how to work with variables, let's discuss two numeric data types, int and double. Before we do that, let's talk about numeric literals. Numeric literals are absolute numbers written in the program. All numeric literals have a data type. For instance, the number 6 and the number 6.5 are not the same data type. Previously, we have seen the int data type in action. We use the int type to represent an integer, essentially a number that cannot have a fractional part. The typical range of an int is about -2 billion to about +2 billion. That is, it can only accept values within this range. A value lower than this range causes an underflow, while a value over this range causes an overflow. In order to define an integer variable, you simply need to use the int data type while declaring or initializing a variable. But what about numbers with fractional parts? For them, we will use the double data type. We will use the double data type to represent floating point numbers. Unlike an integer, floating point numbers are capable of representing numbers with fractional parts. In order to define or initialize a variable of type double, all you need to do is use the data type double. Notice that in this number, the fractional portion is 1/4 that comes after the decimal point. Now let's take a look at a few examples. Given a numeric literal, which data type would be most suitable? A good rule of thumb while deciding the numeric data type in C++ is to look for the decimal notation or the exponential notation. If either is used, you should use the double data type to avoid any information loss. In this example, all three numbers are integers. Thus, they can be represented by an int variable. In this example, 10,000 is not a valid literal since it has a comma between its digits. Do not use a comma as a decimal separator. The remaining numbers 5.6 and 1.0 are both doubles. They cannot be represented by an int because both of them have a fractional part. While one may argue that 1.0 can be represented as an integer, however, remember, an integer with a fractional part of 0.0 as well should be represented by type double to avoid any loss of precision. In this example, you will notice that the number has a letter E in between its digits. This is not wrong. This is called the scientific or exponential notation of a number. This is a way to represent large numbers in a concise manner. The letter E, regardless of the case, differentiates the number into two parts. The portion containing the letter E and the numbers after it constitute the exponent of the number. The number on the left can be written as 5.6 times 10 to the power 2. Notice that the portion before the letter does not change but is now involved in a product with the exponent. Similarly, for the number on the right, the number becomes 1.2 times 10 to the power minus 4. Following a rule of thumb, we see both the exponential notation as well as the decimal notation, and thus the data type for these numbers is a double. Now, let's take a look at a C++ program where we work with both integer and double variables. In this program, first, I'm going to initialize the variable a of type int to the value 10. Then, I'm going to define another variable of type int called b. In a separate statement, I'm going to assign the value of 20 to the variable b. Then, I'm going to print the values of a and b respectively. After that, I'm going to initialize a variable c of type double to the value 10.2. Notice the presence of the decimal symbol, which denotes a fractional part. Then, I'm going to initialize another variable of type double called d to the number represented using the exponential notation. Notice that you can use both lowercase and uppercase character e to denote the exponent. Finally, I'm going to print the values of the variables c and d. Notice that despite the differences in the data types of the variables, the print statements do not differ. Let's go ahead and run this program. Notice that the double variables are printed in a decimal notation. They retain the fractional part. Here in this example, I'm initializing a variable x of type int to the value 3.55, a number with a fractional part. And second, I'm initializing a variable y of type double to an integer literal, 3. And then finally, I'm going to print the values of both of these variables x and y to the screen. What do you expect to appear on the screen? The first number, which is the integer variable x, shows us 3, even though we specified the number as 3.55. This is not surprising, because we mentioned that integer variables are not capable of storing fractional portions in a number. Thus, when you assign 3.55 to the variable x, the fractional portion, which is 55, is completely ignored, and only 3 is stored in the variable x. While for the double variable y, 3 is a perfectly fine initial value, because 3 can always be written as 3.0. Thus, you can initialize double variables to an integer, but you cannot initialize integer variables to a double literal without losing any information.